So how does change in concentration affect equilibrium position of a reversible reaction? The effect of change in concentration on equilibrium position is very straightforward. It's the simplest, right? Remember, every chemical reaction is made up of two components: the reactant and the product. So once you change the concentration of the reactant, it will affect the concentration of the product. That's how changing concentration works. Which is that if you increase the concentration of the reactants, it will definitely increase the concentration of the product. And if you decrease the concentration of the reactants, it will decrease the concentrations of the product. That's how the system will react, right? So what you need to know now is, how do you increase the concentration of the products? How do you increase the concentration of the reactants? How to increase the concentration of reactants. And of course, you know that the opposite of this would be for decreasing the concentration of the reactants. Our focus is on the reactants. One, you can do that by doing what? You add more reactant. If you add more reactants to the equilibrium system, you are increasing the concentration of the reactants, right? Then you can do what? Remove the products as they are being formed. Right? If you remove the products as they are being formed, you are doing what? You are indirectly increasing the concentrations of the reactants, and the system will react to that. Or you can do what? Liquefy the gaseous products. Liquefy the gaseous products as they are being formed, like Haber process, right? You know, it's a complete gaseous system where both reactants and products are gases, right? And when you liquefy the ammonia that is formed, the concentrations of the nitrogen and hydrogen gases will do what? Increase automatically. Are we together? Good. So increase in concentration of reactants. Do what? Shift equilibrium position. To the right, always. Favors the forward reaction. And does what? Increases the yield of the product. Remember, anything that favors the forward reaction will always increase the yield of the product. And the decrease in concentration of the reactants will be the opposite of this. Now, I would like to use a seesaw to explain this. You know a seesaw, right? Fine. You know that a seesaw is a form of what? A balanced seesaw is a form of what? Static equilibrium, right? In this case, the forces on both sides of the fulcrum are equal, right? So it's balanced. Good. Now, this is concentration of the system. because the system is at equilibrium. Remember, the concentrations do not really need to be what? Equal, but they are constant. Remember what? Which means that the system is at what? Equilibrium. If you now increase the concentration of the product, of the reactant, what will happen to the seesaw? Let's say you increase the concentration of the reactants and you decrease the concentration of the product. What do you think will happen? The system will react. How? By moving some of the excess reactants to the product. Can you see? It moves it to the product. So as it does that, it will cause the system, that's the seesaw, to reattain its what? Equilibrium, or establish a new what? Equilibrium, as you will see now. The seesaw will now establish a new equilibrium here, where the concentration of the reactant will have reduced to enable the seesaw to regain or to reattain its equilibrium. Are we together? So this is the new equilibrium now. The same pivot or fulcrum. So this is how increase in concentration of reactants work. Remember that the concentration of the reactants and products do not necessarily need to be what? Equal, but they will be what? Constant. And when they are constant, it's when the system is considered to be what? At equilibrium. Are we together? Now, before we leave this, I would like to use a graph to also explain what we meant by the concentrations of the reactants and products being constant at equilibrium. Let's say this. So you have a graph of concentration against time, for concentration in moles per dm cube, and time in, you like call it minutes, seconds, whatever. At the beginning of the reaction at t equals 0, the concentration of the reactant is maximum, is it not? And as the reaction progresses, it decreases until it levels out, right? So this is the reactant. At time t equals 0, the concentration of the product is 0. And as the reaction progresses, the concentration of the product keeps increasing until it gets to its what? Maximum. This is the concentration of the product. If you look at this graph, at this point where these two curves meet, that is the time at which the concentration of the reactant equals what? Concentration of product. Here, that point, let's call that A. A at, let's call that TA. At TA, right? Concentration of reactant equals what? Concentration of products. But that is not the time at which the reaction attain what? Equilibrium. Because the condition for equilibrium is that the concentrations of the reactants and products would be what? Constant. You can see that after this point A, the concentration of the reactant kept decreasing, while that of the product kept increasing. So that cannot be the point of what? Equilibrium. The point of equilibrium is where they became what? Horizontal. So you can see here, this is the point, and this is the point. So, of course, this is not drawn to scale. At this point, this is the time at which the concentrations of the product and the reactant became what? Constant. So we can call this what? TE, right? That's at TE, concentrations of reactants and products are what? Constant. So, which means that at that point, system attains what? Equilibrium. Are we together? Yes. So, which means that if we eventually change the concentration of any of these guys, if we increase the concentration of this reactant, right? Definitely the concentration of the product will also what? Increase or change, as the case may be, right? So let's look at an example. Let's look at the contact process for industrial manufacture of H2SO4. The reaction between sulfur 4 oxide and oxygen gas to form sulfur 6 oxide in the presence of what? Vanadium 5 oxide. Increasing the concentration of either the sulfur 4 oxide or oxygen gas will do what? Increase the concentration of the sulfur 6 oxide, and vice versa. That is, decreasing the concentration of SO2 or O2, or both of them, will decrease the concentration of SO3. It's that simple. So next would be the effect of a catalyst on the equilibrium position.